Here's a situation where a little bit of knowledge could be misleading. If you have two planets, same density, so you have a small planet here and another planet here that has, say, 10 times the diameter, how does changing the size or the diameter affect gravity on that planet? I think if somebody knew nothing about physics, they might guess that if a planet has 10 times the diameter, then it would have 10 times the gravity. Those little triangles there mean delta, which means change. But if somebody knew some basic physics equations, they would know that as the diameter increases, so does the radius, which means anyone or anything on the surface of that planet is going to be farther away from the center of that planet. And acceleration from gravity is inversely proportional to the square of the radius of that planet. So if you're 3 times farther from the center of that planet, you'll actually have 1/9 of the acceleration from gravity. Also notice the nonlinear relationship between the volume of a sphere or the volume of a planet compared to the radius of that planet, because you have to take the cube root of volume to get your radius. And if we're dealing with two planets that have the same density, then that would mean 10 times the volume will also equal 10 times the mass. So what's the probability that this volume, this mass, and this radius will all even out proportionally so that you can have a linear relationship between radius and acceleration from gravity? So it turns out if somebody knew nothing about these equations and they just guessed that if a planet had twice the diameter, it would also have twice the gravity, that person would be correct. And I'll show the proof of that in this video. And next page. Force equals gravitational constant times mass 1 times mass 2 divided by radius squared. Let's make mass 2 the object or the person that's on the surface of the planet. So force equals mass times acceleration. So mass 2 times acceleration equals gravitational constant times mass 1 times mass 2 divided by r squared. The mass 2's will cancel out. You just end up with gravitational constant times mass of the planet divided by r squared equals your force of gravity or acceleration of gravity. Gravitational constant equals 6.67 times 10 to the negative 11th. We have 3 variables here, radius, mass, and gravity. First thing I got to do is get rid of one of these variables. And next page. Let's change our mass into density times volume. So we got GdV over r squared. How I got this r squared is looking at the radius here of the planet, 3v over 4 pi to the 1/3, 3v over 4 pi to the 1/3, but then we have to square that. And believe me, I made a lot of arithmetic errors in this because it gets even more hairy. This whole thing here becomes 2/3 exponent. You multiply your exponents. And what I'm going to do here is I'm going to go ahead and pull that volume out. So that's volume to the 2/3 out here. And then right here is 3 over 4 pi quantity to the 2/3. Volume to the 3/3 divided by volume to the 2/3. You just subtract your exponent. You end up with volume to the 1/3 right there over what's left of your radius, which is 3 over 4 pi quantity to the 2/3. Now let's isolate our volume here. So I'm going to do a few things at once. I'm going to bring up this 3 over 4 pi to the 2/3, divide by GD. I should say capital G, lowercase d. Take the whole thing to the 3rd power, and then that will give me volume. I actually did 3 things at once there, but you can see we isolated our volume. And next page. Let's turn our volume into radius. So volume equals 4/3 pi r cubed. Go ahead and isolate radius. And it looks like this. All right, now this is where it gets hairy because this whole thing equals radius. See this volume right here, this V? I have to plug in this whole thing right here for V. And there's a lot of exponents and things to carry through, a lot of chances to make mistakes. So I end up with 3 times that big mess right here, and then divide by the gravitational constant times density, and divide that by 4 pi. You can see some of this here. There's your 3, there's your 3. This whole thing right here equals your volume. Your 4 pi goes from right here down to here. You have to take everything to the, let's see here, take everything to the 1/3 power, and there's your 1/3 power right there. Notice here, this is a short division sign. That is a long division sign. The reason that matters is, if this was a long division sign, then this 4 pi would be in the denominator of a denominator, which means it goes up to the numerator. but it does not do that. It, in fact, stays in the denominator. And that is because the 4 pi is underneath a long division sign and not a short division sign. I'm going to start distributing all these exponents through. Notice right here, the GD, for example, we have an exponent 3 and 1/3. That'll cancel out and become 1, so that capital G, lowercase d, stays as a 1 exponent. Let's see, G here, from gravity, that stays as a 1 exponent. 3 over 4 pi to the 2/3, that stays as 2/3. 3, however, 3 will just have 1/3 as the exponent. This 4 pi will stay as a 1/3 exponent. And it's interesting to notice the complexity of this. We have a fraction that is a numerator of another fraction, and that whole fraction is the numerator of another fraction. And in addition, we have an exponent to an exponent to an exponent. And every term will be under a different number of exponents. Next page. That 4 pi I brought up here next to everything else, so it's in the denominator still. Let's go ahead and isolate G, so that'll be R times 4 pi to the 1/3 power, and that should have a parenthesis around it. Multiply R times GD also, and notice here the 3 exponents will turn into 1. 1/3 plus 2/3 equals 1. I'll show the rest on the next page. Continuing through the algebra here, I just take all of this times 4 pi quantity to the 2/3, and it'll look like this. Then I have to divide by 3 to get G by itself. Notice this 4 pi to the 1/3, that 4 pi to the 2/3. Add your exponents, you just end up with 4 pi. And next page. Here's the full equation right here, very simple. Radius times 4 pi times your gravitational constant times the density of the planet. By the way, you can get this density 2 different ways. One is on Wikipedia. Another way is to derive it with the mass of the Earth divided by the volume of the Earth. Mass and volume are also on Wikipedia. I tested them out just to make sure I got the same numbers as Wikipedia for density, volume, and mass and everything. Okay, so what this means is you take the radius of the planet. By the way, Wikipedia gives us as kilometers. You have to turn it into meters, times 4 pi, times your gravitational constant, 6.67 times 10 to the negative 11th, times the density of the planet in kilograms per cubic meter, divide it by 3, you'll get 9.8 meters per second squared, which is the acceleration on Earth. Actually, I almost forgot to, not super important, way back when I started driving all this, notice the G right here, for gravity, acceleration of gravity, goes to an exponent of 1. 3 times 1/3 is 1. So that means as you increase or decrease your gravity, that will increase or decrease the radius proportionally. But I just sorted through it all right here to make it simpler. And next page. What this means is we have the radius of Earth right here is R. That gives us 1 G of gravity, or 1 G of acceleration from gravity. That means if we have 10 times the radius of Earth, then we'll have 10 Gs. If we have half the radius of Earth, then we'll have 1/2 G. Notice how scaling up the mass or the volume of the planet doesn't change anything. And that is because density is mass divided by volume. So because we're dealing with the same density, that means if you have 10 times the mass, you'll also have 10 times the volume. So changing the mass doesn't matter because we're left with the same density. So density and radius are the only 2 things that matter in this equation that affect your gravity.